Okay, good morning and welcome to the online portion of this. We're going to be working on schematics this morning, okay? So the reason why schematics are important, we're going to talk about ISO schematics. And schematics, what we're going to do here today, are important for two reasons. Okay, one, it's important to know the schematic symbols and understand how to use them and read a schematic blueprint. But the second thing is, as we go through this, we're going to be talking about important hydraulic principles and helping you further understand how a system works and all the components work together in the system. So it's a very important lab for that, and it's going to achieve two of your learning outcomes. Okay? So I mentioned ISO schematics. That stands for ISO, and that's the International Standards Organization. So this is a group of people that got together to try and find a standard set of symbols so that no matter whether you're in Canada, the United States, Japan, Russia, doesn't matter where, you can open up a manual and you can decipher what's in the hydraulic system by the schematics. So that's the need for having these ISO symbols. So they're a global set of symbols that can be used. All right, so you've got your lab assignment. It's on D2L, and we're going to go through it. There's 8 questions, so we're going to start and talk about each of the different questions. And the beauty of this is that you can stop it at any point and back up and replay it. And if there's questions at any point in time, you can email me and ask me to explain further on some of the different points that you didn't understand. All right, so let's go to question 1. All right, so what I'm going to do is zoom in on here, so you won't be able to see my face for this, but you'll be able to hear me, and we'll talk about each one of these. And then when it comes time that I need to explain questions 7 and 8, then we'll zoom the camera back out so you can see me. All right, so question 1, what is the maximum pressure seen at the stabilizer tilt cylinders? Okay, so we'll move this down. There we go, the stabilizer tilt cylinders. Okay, so this represents your directional control valve. Here's 1, 2, 3, 4, 5 different handles that would be in that control valve. And this component enclosure, you're going to hear us talk about component enclosure several times. This long and short dashed line that goes all the way around means that if we took this and actually picked it up, we could set that right on the bench. Okay, so this is our directional control valve with all of its handles. So all of those symbols in there look very confusing, but you just have to know that that's what we have worked on the bench many, many times, okay, and it's not complicated. This is showing you a relief valve, and that is just a cartridge that screws in to the side of the directional control valve. And like I said, these are the different stacks, spools, different names you've heard them called, okay? So that is our directional control valve. Now here we've got our stabilizer tilt cylinders. So when we set the rig up and we get it all leveled, we're doing it with these stabilizers. Okay, so what is the maximum pressure seen at the stabilizer tilt cylinders in PSI? We have to look at where the oil can escape. Okay, oil takes the path of least resistance. The oil is going to be pushed into the circuit and build up and build up and build up until it can escape. Okay, and in this case, the only place that it can escape in this component is through that relief valve, but we also have a main relief valve in the system, which over here, this is the pressure line, okay, coming from our pump. This one's at 2,500 PSI. So this is our main relief valve that's right behind the pump at 2,500, and then we have another relief valve in the actual directional control valve, and it's set at 1,500. So path of least resistance, okay, it's going to get out of this relief valve at 1,500 PSI. So that's the maximum pressure that we can build up on the stabilizer tilt cylinders is 1,500 PSI. All right, number 2. Why is the torque gauge reading pressure on one side of the rotation motor only? Okay, so bring that down. All right, so here's our rotation motor. And you can see that the motor has the symbols to show both directions, so it's a bi-directional motor. It'll turn back and forth. And that makes sense to us because the rotation, the feed, when we start to drill, we're drilling down into the ground. That's one direction, and we want to, when we want to back it up and come out counterclockwise, okay, we need to be able to turn in both directions. That's very straightforward. Nobody has a problem with that, I'm sure. Okay, but the torque gauge, what the torque gauge is going to tell us is how hard it is to turn that motor. Okay, so when we start to drill and we just have the head turning and there's no resistance, that's going to be very low. The pressure is going to be very low. But then as the bit goes into the ground and starts to get resistance, this torque gauge is going to start to go up. If we get into very, very hard rock, the torque gauge is going to go way up. Okay? Then if we break through and we get into some sandy conditions, now the torque gauge is going to go down because it's much easier drilling in that. Okay? So the reason we need the torque gauge is for operator feedback. So you can watch that pressure gauge and you can tell what's happening down in the hole based on what the pressure is doing on this gauge. Okay? So now we've talked about what the torque gauge does and why it's important. Okay? The question is, why isn't there one on both sides? The reason why you don't need one on the back is because if you're backing out, you're breaking rods loose, things like that, you really don't care what the pressure is and how much torque it needs to break those rods loose. Okay? So that's not important to have one on the reverse direction. We only need it when we're drilling. Okay? Now, while we're on that, we've got this funny fork-shaped line that comes in. It's attached to the motor and it comes down here and it attaches to the outlet. So what that's called is a case drain. I always say like a case of beer. Okay, it's a case drain. So this motor is in a case, okay, and there's internal leakage built into every component, all through it. It's meant to do that. So we've got oil that's leaking out and it's building up inside that case. So when it builds up in there, if we don't let it go and get rid of it, it's going to build up pressure and it's going to blow out a shaft seal. So that's why we have this drain, and it's a very low pressure line. There's really no resistance on it. It just allows that oil to escape and come back in and get away and back to tank. So there's really no pressure on that line. It just allows it to get away so it doesn't build up. So that's called a case drain, and that's on every hydraulic motor to allow it to get away. All right, so question 3. When high pressure is generated in the auger circuit, does oil escape through the main relief or the circuit relief? All right, so here's our auger circuit. Once again, we go back to where the relief valves are. So here's the main relief in the valve, and it's set at 2500 psi. This is our component enclosure, which shows that this is a DCV. Now, we have these relief valves, which are called circuit reliefs, because these are just controlling the pressure in the circuit. All right, so after the valve here, when this valve is in the neutral position, work ports A and B are blocked. So there could be external forces built up in this. We need circuit reliefs. Okay, so they are set at 1500 psi, which means oil goes path of least resistance. As soon as it builds up to 1500 psi, that's when they're going to open. And they don't drop the pressure. A relief valve doesn't drop the pressure, but it prevents the pressure from going any higher. And in this case, 1500 psi is the cutoff limit. Okay, so both sides of that auger can only build up 1500 psi because they will never build up to 2500 in that circuit. Okay, so that was question 4. Question 5. What is the maximum pressure seen at the base end of the clamp cylinder? Okay, here's our clamp cylinder. So, there's the base end of the clamp cylinder. Once again, come down, look at the circuit relief. This will be in your manual. It tells you what it is. If there isn't a number written on there just like that, you look back through the legend of your manual and it should tell you right in there. So this one's at 300 psi. So that's the base end, that's the path of least resistance, and it's going to escape at 300 psi. And then the second part of this question, why is it different than the rod end? Okay, so we look here, you know from Hydraulics 1 that the rod end of the cylinder has less surface area than the base end. Okay, and if you have the same amount of pressure going into that cylinder, you're going to have different force on each side of the cylinder because of the surface area. Okay? In this case, on the clamp, we are doing two things here. We're first of all reducing the pressure so that it doesn't crush and damage your drill rods. But then secondly, we want to have the same force in each direction of that clamp cylinder. Okay, so it's the exact same force in both directions. So in order to obtain the same force in both directions, we need to put more pressure in to the rod side. It has less surface area around the rod, so we need to put more pressure to it so that the force is the same in both directions. Okay, so that's why we have two different pressures, okay, to obtain the same force. And it's just a simple calculation. You plug the numbers in and it tells you what the force will be. So in this case, 300 and 400. All right, question 6. What is the flow available from the main hydraulic pump? This one's fairly straightforward. Now, as I said, if there's not a number on it, you would consult, go back into the manual, and you can see it will tell you in the literature. And in this case, I went back through and found it, and it says the main hydraulic pump is 12 gallons per minute. So I wrote it on there for you. But it wasn't on this one. Okay, you had to go search for it. And while we're on that, you can see the symbol for this, the ISO symbol for that, shows that it's a fixed displacement pump and it's a positive displacement pump. So a positive displacement pump means that the pump will push oil into a confined system. Okay, it has that ability. So it's positive displacement, it can push into a pressurized system. And it's fixed displacement, meaning that if it's turning at one constant RPM, like an electric motor would turn it, okay, then it will give a constant gallons per minute, constant flow rate all the time. Okay. So fixed displacement, positive displacement out of that pump. All right, so now we're going to get into question 7. This one, question 7 and question 8 get a little more complicated, so I'm going to talk with my hands for a few minutes. So what component is shown by the ISO symbol in the component enclosure located in the left track drive circuit? It's called a counterbalance valve. Counterbalance valve. Okay? And I want to first explain what a counterbalance valve does to you before we go back to the schematic. So, the purpose of a counterbalance valve is to provide control for the track motors. If you have a machine, let's say you have an air track drill, okay, it has tracks, and there's a track on each side, obviously. Each one of those has a drive motor, okay? They will turn independently, so you could spin it around on a dime, you can turn it in a big arc, okay, or you can go straight ahead. So you have two drive motors. Now, the reason for a counterbalance valve we're going to get to in a minute, but first of all, let's talk about, you walk up to the air track drill and you take a hold of the levers and you start to move forward. So you're putting oil pressure to the track motors, and the tracks will start to turn and the rig will move. And that's all fine, that's not complicated at all. And now we get to a hill and we start to go up the hill, and the pressure rises against those motors because it's getting harder to push that rig up the hill, but that's no problem. We get lots of pressure in the system, so we go up the hill. Everything's good. But as soon as we crest the hill and we start to go down, now we don't need the oil pressure to move the rig because the weight of the rig itself is going to start to push that. It's going to take off and run down the hill on its own weight. It doesn't need your oil pressure anymore to turn those drive motors. So now the weight of the machine is going to start pushing it. And the only thing you have holding it back, there's nothing, because the oil can easily get back to tank. So now you could have an overspeed situation where this thing takes off down the hill. So we're going to put a counterbalance valve into this to provide us some control over these track motors when they're going down a hill. So now that you understand why the counterbalance valves were bolted on to each one of those track motors, those hydraulic motors, now that you know what they're for, I'm going to switch over to the schematic and show you how that works. Okay, so the counterbalance valve are going to provide you control over those hydraulic motors when the machine is going down a hill. Okay, I'm going to move this down a little bit. So here are the two handles that I told you about. I have a hold of those and I start to move ahead. Doesn't matter whether I'm going up the hill at this point, I'm driving straight ahead. So I take a hold of these two handles and I move them. So now I take pump oil and I direct it, let's go up the right hand side. So we go up here and the oil turns and comes along and hits this normally closed valve. Okay, so the oil can't get through that valve. So it scoots over here and goes through the check valve. Okay, and turns and goes here against each of the two motors. Okay, that's fine. There's also a passageway here. It's just a pilot line that goes across and no oil flows through it. Its pilot lines are just signal pressures. So that's full of oil. So we have our oil come around here and it starts to turn the drive motors and then bang, it hits these valves, okay? Also inside, this is the counterbalance valve. So it hits against there and it's blocked. So the motors can't turn, okay? This pressure starts to build up from the pump, okay, that's going around here, builds up, builds up. Now this pilot signal is also building at the same time, and the pilot signal is now high enough to overcome the spring, and it shifts this spool aside, and now the oil is allowed to get out and go back to tank. So now the track motors will drive straight ahead. But we had to build up oil pressure in order to open that counterbalance valve and allow us to move. Okay, so we're driving straight ahead. We've got this pilot pressure here that's holding the valves open and allowing us a return flow path back to tank. And that's allowing the motors to turn. So now this is where we go up the hill. That doesn't change, but when we go over the crest of the hill and we start to go down the hill, the weight of the machine wants to take it and run with it. Okay? And when that happens, now our oil pressure drops because we don't need that pump pressure to move this. The machine is turning that. So when it does that, this oil pressure drops from the pump. The pump can't keep up now. So this oil pressure drops, and at the same time the pilot pressure also drops and these valves slam shut. So if we looked at this in slow motion, we start to go down the hill and it gets fast and then bang, it stops dead. Okay, and now the pump has to produce oil pressure in order to make it move again. So then it says, all right, you've got control of it again. The oil pressure catches up and builds up, and this can slide over again and it starts to move. So then it goes, but then starts to overspeed and these valves slam shut. So if we were in slow motion, it would be opening, shutting, opening, shutting, opening, shutting as it goes down the hill. And the machine would be jerking, 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 jerking. But in real life, these valves move so fast back and forth that all you see is a steady movement down the hill as it goes, because the counterbalance valve will shuttle back and forth to maintain the pressure and keep it under control. Okay, so those little valves are shuttling back and forth and keeping it moving at a steady speed. So it can't overspeed, it can't get away from you, because as soon as it starts to, these slam shut and the return flow path is blocked off and both motors stop dead. Okay, so that's what the purpose of the counterbalance valve is, and that's how it works. It's just working off pilot signals, and this is bolted right onto the side of the track motor, and usually it's only about 4 inches long, and it has a little spool through it, and it has spring tension on each end so you can adjust it. It's a very simple system, but very effective. All right, so that's question 7. And the last one, explain the purpose of the check valve placed before each DCV spool in the drilling portion of the schematic. Okay. So here is the check valve, and it's placed before each DCV spool. So remember, each spool has a handle attached to it, okay, and works different functions. All right, so this is what we're going to talk about. And once again, I'm going to turn on the light and I'm going to explain to you what the check valve does, what its purpose is, and then we'll come back to the schematic. All right? So, for this, let's picture a farm tractor. All right? On the farm tractor, we have 2 handles. We have one handle for raising the boom and lowering the boom, okay? And the other one would be for the bucket to dig and dump. All right? So we've got our bucket on the end, and we are going to go in and pick up some gravel. So we drive into the pile of gravel, and I grab onto the lever and I curl the bucket back, and I've got a big bucket full of gravel. Now I grab the other one and I pull, and this big bucket full of gravel is lifting, 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 okay? And then I decide it's high enough, so I let off on the handle. And now work port A and work port B are both blocked, so that load of gravel, that bucket full of gravel, stays up in the air. Okay? And I drive over to the truck. All right? So it's taking a certain amount of pressure to hold that bucket full of gravel up in the air. Let's say it's taking 2,000 psi to hold that gravel up in the air. All right? So I drive over to where the dump truck is. Well, now, okay, I was driving over there, and it's an open center system, so the pump oil that was rotating through back to tank was at basically 0 psi. Open center system, 0 psi when it's in neutral. But I had 2,000 psi stuck in the base end of those cylinders holding that gravel up. So I get over to the dump truck and I decide, okay, I have to lift it up higher to get over the side of the dump truck. So when I pull on the handle to raise that up higher, I have 2,000 psi in the base end of those cylinders, which was holding the gravel up in the air, and I have 0 psi in the main line coming from the pump. So all of a sudden, as soon as I pull that handle, they instantly join, okay, they're connected, and now they meet in the middle, the pressure will drop down to 1,000 psi. And 1,000 psi isn't enough to hold that bucket full of gravel up. So if, once again, slow motion, as soon as I pulled that handle, you would see it drop. And then the pump will start to catch up and it will go 1200, 1500. And when it gets to 2000 PSI and 2000 and above, now it can start to raise that. And it can raise it and lift, and I can dump it in the truck. But we don't want that drop when we first pull the lever, okay? We want our load to stay in the same place until the pump pressure builds and can raise it further, okay? We don't want that drop. So that's why we put a load check valve in the system to hold that, okay? So let's go to the schematic and we'll explain that further. Okay, so forget about what these do. Let's go back to talking about the tractor. Let's look here. Okay, here's our handle that I was talking about, and this is what I would pull if I wanted to lift it further. So out here, this is the work port that's holding that bucket up in the air with all the gravel in it. And we said that it was at 2000 PSI trapped in there, holding that bucket full of gravel up. Okay? Now, when I pulled on the lever, this main line was at 0. So, when it connects, it's going to drop down somewhere around 1000 PSI and the bucket will drop. But by putting in this load check valve, okay, that 2000 PSI tries to go back in the line and it slams the check valve shut. So now the pressure line, because you moved the spool, it's blocked through the center. It has no choice but to come over against the load check. But the load check is slammed shut by 2000 PSI. So the pressure here starts to build from 0 to 100 to 500 to 1500 to 2000. Still can't get through, but as soon as it hits 2001, it can overcome the check valve and start to push into that work port, and our bucket goes up, right? So that's what the load check is doing. It's holding the pressure in the work port until pump pressure is able to catch up, okay? And it's drawn as a check valve, but it's just a little plug that's put right in, screwed right into the side of the directional control valve. It's very small and it screws in there, and there's one screwed into each one of those DCV spools, and that's your load check. All right, so like I said, we've gone through the 8 questions and you shouldn't have any trouble with those, but if you do, feel free to email me and we'll go through it, or I've given you my phone number. You can call me and we can discuss it like this over the phone and help clear it up for you. Okay? Have a great day. Thank you.